What if I told you that right now, as you watch this video, there are photons of light racing away from Earth at 186,000 miles per second that will never, ever reach their destination? Not because something blocks them, not because they'll run out of energy, but because the space they're traveling through is being created faster than they can cross it. These photons are trapped in an expanding cosmic prison, and they don't even know it? Here's something that will absolutely shatter your understanding of reality. There are galaxies, billions of them, that are moving away from us faster than the speed of light right now. Not through space, but because space itself is expanding. And the light from these galaxies? It's running on a cosmic treadmill, sprinting as fast as the universe allows, but getting nowhere. The photons are exhausted, stretched into invisibility, screaming silently into a void that's growing faster than they can possibly traverse. But here's the really disturbing part. If you were standing on a planet in one of those galaxies right now, looking back at Earth, you'd see the exact same thing happening to us. From their perspective, we're the ones being swept away into cosmic darkness. The light we're sending out to say, "We are here," will never reach them. Ever. Not in a billion years. Not in a trillion years. Never. The universe has an edge, but it's not what you think. It's not a wall. It's not a boundary you can touch. It's a horizon of possibility itself. A line in space-time beyond which the fundamental laws of physics prevent any communication, any connection, any relationship whatsoever. And that edge is coming for us. Every second, thousands of galaxies slip beyond this horizon, disappearing from our universe forever, as if they never existed at all. In the next 3 hours and 20 minutes, I'm going to take you on a journey that will fundamentally change how you see reality. We're going to explore the edge of everything, the boundary between the knowable and the unknowable. And we're going to answer one of the most profound questions ever asked. Can light escape the universe's edge? The answer is going to break your brain in the most beautiful way possible. Before we dive deep, I need you to do something. Hit that like button right now and subscribe, because what we're about to explore together is going to require commitment. This isn't a surface level explanation. We're going deep, really deep. Also, drop a comment telling me what country you're watching from and what time it is for you right now. I want to know how far across this pale blue dot our community reaches. Are you watching this at 2 a.m., unable to sleep because the universe keeps you awake? Or is it a lazy Sunday afternoon? Tell me your story. All right, let's start with something simple that will immediately become complicated. Light. You know what light is, right? You've seen it your entire life. It illuminates your room. It comes from the sun. It bounces off this screen into your eyes right now. Simple stuff. Except light is the weirdest thing in the entire universe. And everything strange about our cosmos flows from light's bizarre properties. Light travels at 299,792,458 meters per second in a vacuum. We usually round this to 300,000 kilometers per second, or about 186,000 miles per second. This isn't just fast. It's not even just really fast. It's the cosmic speed limit, the maximum velocity at which anything in the universe can travel, the speed at which causality itself propagates through space-time. But here's your first mind-bending moment. Nothing can travel faster than light, but light itself doesn't experience time. From a photon's perspective, if a photon could have a perspective, the moment it's emitted and the moment it's absorbed happen simultaneously. A photon that travels from a distant galaxy for 13 billion years experiences that journey as instantaneous. Zero time passes for the photon. Think about that. The photon exists in a state where its beginning and ending are the same moment. It's born and dies in the same instant of its own time. This is what Einstein's special relativity tells us happens at the speed of light. Time stops. Distances contract to zero. The entire universe, from the photon's frame of reference, is compressed to a single point. Every photon that has ever existed, from the first light of the Big Bang to the light bouncing off your screen right now, exists in an eternal present moment, and now that encompasses everything. Think of it like this. Imagine you're an immortal being who never ages. You step onto a magical train that travels at the speed of light. From your perspective outside the train, years pass, decades, centuries. But if you could hitch a ride on that train at light speed, you'd step off at your destination having aged not at all, having experienced zero passage of time. The journey would be instantaneous for you, no matter how far you traveled. That's what every photon experiences. Every single one. Now, here's where things get interesting. If light doesn't experience time, and if light is what carries information through the universe, what does that mean for the structure of reality itself? It means that the universe isn't just a three-dimensional space that exists through time. It's a four-dimensional space-time, and light traces out the boundaries of what can possibly be connected to what. The speed of light isn't just about light. It's about the speed of causality. It's the speed at which causes can produce effects. If I'm here on Earth and I want to affect something on Mars, the absolute minimum time that has to pass is the light travel time between Earth and Mars, about 3 to 22 minutes depending on our orbital positions. Nothing I do here can affect Mars any faster than that. Not gravity, not quantum entanglement, not any signal whatsoever. The speed of light is really the speed of cause and effect, the speed at which reality updates itself. This matters for our question about light escaping the universe's edge because it means that the edge we're talking about isn't just a physical boundary. It's a causal boundary. It's the edge of what can possibly affect what, the boundary between regions of space-time that can communicate and regions that are forever separated. Let me introduce you to the first of our scientific heroes, Ole Rachmer, a Danish astronomer who in 1676 made one of the most important discoveries in the history of science. He figured out that light has a finite speed, and he did it by watching Jupiter's moons. Rachmer noticed that the eclipses of Jupiter's moon, Io, appeared to happen earlier when Earth was moving toward Jupiter, and later when Earth was moving away. He realized this wasn't because Io's orbit was irregular, but because light took time to cross the changing distance between Earth and Jupiter. This was revolutionary. Before Rachmer, most scientists thought light traveled instantaneously. Galileo had tried to measure the speed of light by having two people with lanterns stand on distant hilltops, uncovering their lanterns in sequence and trying to measure the delay. It didn't work because light is too fast and the distance is too short. But Rachmer had the entire solar system as his laboratory. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. He was pretty close. The actual time is about 16.5 minutes. What Rachmer discovered was that the universe has a speed limit, that information takes time to propagate, that what we see in the night sky isn't the present moment, but the past. The light from the sun takes 8 minutes and 20 seconds to reach Earth. When you look at the sun, you're seeing it as it was 8 minutes ago. If the sun exploded right now, we wouldn't know for 8 minutes. We'd continue seeing sunlight, feeling its warmth, living our lives under a sun that no longer exists for 8 full minutes before the darkness arrived. The nearest star to us, Proxima Centauri, is 4.24 light-years away. The light you see from it tonight left that star in early 2021. You're not seeing the star as it is now. You're seeing ancient starlight, a photograph from the past. Look at a star 100 light-years away, and you're seeing the 1920s. Look at a star 1,000 light-years away, and you're seeing the Middle Ages. Look at a galaxy 100 million light-years away, and you're seeing the age of dinosaurs. The night sky isn't a window to the present. It's a time machine to the past. But here's what's about to blow your mind. If the universe is expanding, and if distant parts of the universe are moving away from us, what happens to light traveling through that expanding space? Does it get stretched? Does it get tired? Can it ever reach its destination if the space it's traveling through is growing faster than it can cross? These questions lead us directly to the edge we're hunting for. But first, we need to understand what we even mean by the edge of the universe. Is there a place where space ends? Is there a wall? Is there an outside to the universe? Or is the edge something far stranger than we can imagine? Before we answer that, I need you to engage. Pause the video right now and think about this question. If light doesn't experience time, and if the photons that enter your eye from distant galaxies have traveled billions of years but experienced zero time, what does that say about the nature of reality? Is there even an objective now that spans the universe? Drop your thoughts in the comments. And if you haven't subscribed yet, do it now. We're just getting started, and it gets so much weirder from here. Let's talk about edges. You live on Earth, which is a sphere. You can walk in any direction on Earth's surface forever and never hit an edge. The surface is finite. You can only walk so far before you come back to where you started, but it's boundless. There's no boundary, no place where the surface ends. This is because Earth's surface is a two-dimensional space that's curved in a third dimension. Now, here's the key insight. The universe might be the same way, but with one more dimension. The universe is a three-dimensional space that might be curved in a fourth spatial dimension. If you could travel fast enough, long enough, in a straight line, you might come back to where you started. The universe could be finite but boundless. No edges at all. Just like Earth's surface, but one dimension higher. This possibility was first proposed seriously by Einstein in 1917, just 2 years after he published his general theory of relativity. Einstein realized that space itself could have a shape, that it could be curved, that matter and energy warped the fabric of space-time. He proposed a static universe, one that was closed and spherical in its spatial dimensions, finite but without boundaries. There was just one problem. Einstein's equations predicted that this universe shouldn't be static. It should either be expanding or contracting. Gravity would pull everything together unless something pushed outward. Einstein was so convinced the universe was static that he added a term to his equations, the cosmological constant, a kind of anti-gravity that would keep the universe balanced and unchanging forever. It was his biggest blunder. Well, he called it his biggest blunder, though it turns out he might have been more right than he knew. But we'll get to that. In 1929, Edwin Hubble, an American astronomer working at the Mount Wilson Observatory in California, made a discovery that would revolutionize our understanding of the cosmos. He was studying distant galaxies, measuring their light, and he noticed something peculiar. The light from these galaxies was shifted toward the red end of the spectrum. The more distant the galaxy, the more extreme the redshift. This redshift is the Doppler effect applied to light. You know the Doppler effect from sound. An ambulance siren sounds higher pitched as it approaches you and lower pitched as it moves away. Light does the same thing. Light from something moving toward you is blue shifted, compressed shorter wavelengths. Light from something moving away is red shifted, stretched to longer wavelengths. Hubble found that distant galaxies were all red shifted, and the farther away they were, the faster they were moving away from us. This could only mean one thing: the universe is expanding. Not just locally, not just in one direction, but everywhere uniformly. Every galaxy is moving away from every other galaxy. Think of it like a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from every other raisin. If you're a tiny person standing on one raisin, you'd see all the other raisins moving away from you. The ones that are farther away would be moving away faster because there's more expanding dough between you and them. But here's the critical part. No raisin is special. Every raisin sees the same thing. Every raisin thinks it's at the center of the expansion. That's our universe. We see distant galaxies moving away from us, and we might think we're at the center of the universe. But we're not. We're just another raisin in the cosmic bread. An alien on a distant galaxy would see the exact same thing we see. All galaxies moving away from them, with the most distant ones moving away fastest. Now, here's where things get crucial for our question. If the universe is expanding, that means it was smaller in the past. Wind the clock back far enough, and all the galaxies were closer together. Keep going back, and everything was squeezed into an increasingly smaller volume. Go back 13.8 billion years, and everything in the observable universe was compressed into a single point of infinite density and infinite temperature. The Big Bang. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Space began expanding from that initial singularity, and it's been expanding ever since. But here's the really weird part. The Big Bang happened everywhere. It didn't happen at a particular location in space. It happened at every location in space simultaneously, because all of space was compressed to a point. The Big Bang happened right where you're sitting right now. It happened on the other side of the planet. It happened in the most distant galaxy we can see. Every point in space was once the point of the Big Bang. So if the universe is expanding uniformly in all directions, and if this expansion started from a single point 13.8 billion years ago, does that mean the universe has an edge? Does it mean there's a place where the expansion ends, where beyond that lies nothing, not even space? Not necessarily. Here's another mind-bending moment. The universe can be infinite even though it's been expanding for a finite time. How is that possible? Because the universe was always infinite. Even at the moment of the Big Bang, space was infinite. It was infinitely dense and infinitely hot, but still infinite. Then it expanded, becoming less dense, cooling down, but still infinite. An infinite space that's expanding remains infinite, just less dense. I know that sounds insane. How can something infinite grow? But mathematically, it works. Imagine an infinite line stretching forever in both directions. Now imagine every point on that line moving away from every other point. The line is still infinite, but the distance between any 2 points is growing. That's an expanding infinite space. But there's another possibility. The universe could be finite but boundless, like Earth's surface, but in 3 dimensions instead of 2. This would be a closed universe, one where space curves back on itself. In this scenario, the universe has a finite volume, but no edge. Travel far enough in one direction, and you'd eventually come back to where you started, like Magellan circumnavigating the globe, but in 3D space. So which is it? Is the universe infinite or finite? Does it have an edge or not? Current measurements suggest the universe is flat, or very nearly flat, meaning it's probably infinite. But we can't be sure. The observable universe, the part we can see, is finite. It's a sphere about 93 billion light years in diameter, centered on Earth. But beyond the observable universe? We don't know. It might be infinite. It might be finite, but much larger than we can see. It might even be one of many bubble universes in an infinite multiverse, but that's a whole other rabbit hole. What we do know is this. There is an edge to what we can observe, and that edge is very real. It's not an edge of space itself, but an edge of visibility, an edge beyond which light cannot reach us. And that edge, my friends, is about to become the focus of our entire investigation. But I'm getting ahead of myself. Before we can understand this observational edge, this cosmic horizon, we need to talk about the speed of the expansion. Because here's where things get truly wild. Distant parts of the universe aren't just moving away from us. They're moving away faster than light. Wait, what? I just told you nothing can move faster than light. That's the cosmic speed limit, the universe's fundamental law. How can galaxies be receding faster than light? Here's the trick. Special relativity says nothing can move through space faster than light. But general relativity, Einstein's theory of gravity and spacetime curvature, allows space itself to expand at any rate. There's no speed limit on the expansion of space. Galaxies aren't moving through space faster than light. They're being carried along by expanding space, and that expansion can happen at any speed. Think of it like a river. If you're swimming upstream in a river, you can never swim faster than your maximum swimming speed. That's special relativity. But if the river itself is flowing faster than you can swim, you'll be carried downstream even if you're swimming forward as hard as you can. That's general relativity and cosmic expansion. This is called the Hubble flow, named after Edwin Hubble. And the rate of expansion is given by the Hubble constant, which is currently measured at about 70 kilometers per second per megaparsec. Let me break that down. A megaparsec is about 3.26 million light years. The Hubble constant means that for every 3.26 million light years of distance, space is expanding at an additional 70 kilometers per second. So a galaxy 3.26 million light years away is receding at 70 kilometers per second. A galaxy 32.6 million light years away is receding at 700 kilometers per second. A galaxy 326 million light years away is receding at 7,000 kilometers per second. At some distance, the recession velocity equals the speed of light, 300,000 kilometers per second. That happens at about 4,200 megaparsecs, or roughly 14 billion light years. Beyond that distance, galaxies are receding faster than light. Not because they're moving through space faster than light, but because the space between us and them is expanding faster than light can traverse it. And this brings us right back to our original question. If light is trying to reach us from these galaxies, can it succeed? If the space between us is growing faster than the photon can cross it, is the photon doomed to fail? And even more disturbing, if we send light toward these distant galaxies, will it ever reach them? Or is it like trying to swim upstream in a river flowing faster than you can swim, doomed to make progress relative to the water, but still being swept backward relative to the shore? The answer is subtle and beautiful, and deeply weird. And to understand it, we need to introduce another hero of our story, George Gamow, the Russian-American physicist who in the 1940s predicted the cosmic microwave background radiation, the afterglow of the Big Bang itself. Gamow realized that if the universe began in a hot, dense state, it would have been filled with intense radiation. As the universe expanded and cooled, this radiation would still be there, but redshifted, stretched by the expansion to much longer wavelengths. He predicted we should see this ancient light as a faint microwave glow coming from all directions in space. In 1964, Arno Penzias and Robert Wilson, two physicists at Bell Labs, accidentally discovered exactly what Gamow predicted. They were trying to eliminate noise from a radio antenna and kept detecting a persistent background signal from every direction. They thought it might be interference, maybe even pigeon droppings on the antenna, but it was real. It was the cosmic microwave background, or CMB, light from just 380,000 years after the Big Bang, stretched by cosmic expansion from visible light to microwave wavelengths over 13.8 billion years of travel. This discovery confirmed the Big Bang theory and gave us a window into the early universe. But it also revealed something profound about the edge we're searching for. The CMB comes from a specific distance, about 46 billion light years away in all directions. Wait, how can something be 46 billion light years away if the universe is only 13.8 billion years old and light has only had 13.8 billion years to travel? Because space has been expanding while the light has been traveling. When the CMB was emitted, those regions were only about 42 million light years away. But in the 13.8 billion years it took the light to reach us, the universe expanded, stretching the distance. Now those same regions are 46 billion light years away. The light has traveled 13.8 billion light years, but its starting point has been carried even farther away by expansion. This is the edge of the observable universe. It's not an edge in space, but an edge in time. It's a horizon beyond which we cannot see, not because light can't travel, but because light hasn't had enough time to reach us yet. Beyond this horizon, there may be infinite universe, but we can't observe it. Not yet, maybe not ever. And here's the kicker. This horizon is growing. Every second, light from more distant regions enters our observable bubble. But at the same time, the accelerating expansion of the universe is pushing more distant regions beyond a different horizon, one they can never cross. Ever. Are you starting to see the edge we're hunting? It's not where space ends. It's where possibility ends. It's the boundary between what can communicate with us and what cannot, between the observable and the forever hidden. And light, despite being the fastest thing in the universe, cannot escape from beyond this edge. I need you to stop and process that. There are regions of the universe, real places with real galaxies and real stars and maybe real civilizations that are forever cut off from us. The light they send out, no matter how long it travels, will never reach us. And the light we send out will never reach them. We are causally disconnected, separated by an expanding ocean of space-time that neither light nor information can cross. If you're feeling a bit of existential vertigo right now, good. That means you're understanding the magnitude of what we're discussing. Hit that like button if your brain hurts in the best possible way. And if you haven't subscribed yet, subscribe now, because we're about to go even deeper. Let's get specific about this edge. Cosmologists call it the cosmological event horizon, and it's currently located at about 16 billion light years away from us. This is different from the edge of the observable universe at 46 billion light years. The observable universe contains everything we can currently see, including light from the early universe that's had 13.8 billion years to reach us. The event horizon is about what we could ever see in the future, even if we wait forever. Here's the distinction. Light from just beyond the current event horizon will eventually reach us, but it will take an extremely long time. And by the time it arrives, it will be so redshifted, so stretched by expansion, that it will be almost undetectable. Light from beyond the event horizon will never reach us, no matter how long we wait. The expansion of space will forever keep it at bay. Think of it like this. Imagine you're standing on a long moving walkway at an airport, the kind that helps you walk faster. Now imagine the walkway is accelerating, moving faster and faster. If you're already on the walkway, you'll reach your destination. But if you're trying to walk onto the walkway from the outside, and if the walkway is accelerating away from you faster than you can walk, you'll never get on. You'll walk and walk, making progress relative to the ground, but the walkway will recede faster than you approach. That's what happens to light beyond the event horizon. But wait, there's more complexity here. I said the universe's expansion is accelerating. That needs explanation, because it's one of the most shocking discoveries in modern cosmology. For most of the 20th century, cosmologists assumed the expansion of the universe was slowing down. Gravity should be pulling everything back together, right? The expansion started with the Big Bang, but gravity should be applying the brakes. We thought the key question was whether the universe had enough matter for gravity to eventually reverse the expansion and cause a big crunch, or whether it would expand forever, but at an ever slower rate. Then in 1998, two teams of astronomers studying distant supernova made a discovery that shocked everyone. The expansion of the universe is accelerating, not slowing down, speeding up. The universe is expanding faster and faster as time goes on. Let me introduce you to our next heroes, Saul Perlmutter, Brian Schmidt, and Adam Riess. These three physicists led the teams that discovered cosmic acceleration. They were studying Type Ia supernovae, which are exploding white dwarf stars that always have the same intrinsic brightness. This makes them standard candles. If you know how bright they really are, you can determine how far away they are by measuring how bright they appear. What they found was that distant supernovae were fainter than expected, meaning they were farther away than they should be based on the expansion rate needed to explain the Hubble constant. The only way to make sense of the data was if the expansion was accelerating. Galaxies that were already moving away from us are moving away faster and faster as time goes on. This discovery won them the Nobel Prize in Physics in 2011, and it forced cosmologists to confront a disturbing fact. We don't know what 68% of the universe is made of. We call it dark energy, and it's some kind of energy that fills all of space and pushes space apart, counteracting gravity. It's the reason the expansion is accelerating. The leading candidate for dark energy is Einstein's old cosmological constant, that fudge factor he added to his equations to keep the universe static. He thought it was his biggest blunder when Hubble discovered expansion. But now it's back, except instead of balancing gravity to keep the universe static, it's driving an acceleration of the expansion. Here's what this means for our question about light escaping the edge. The event horizon I mentioned at 16 billion light years? It's not moving. In a universe with accelerating expansion, the event horizon reaches a maximum size and stays there. That's different from a universe with decelerating expansion, where the event horizon would keep growing as more distant light eventually reaches us. In our universe, with dark energy, the event horizon is essentially frozen. Galaxies that are outside this horizon now will never communicate with us. Galaxies that are just inside will eventually cross out beyond it, slipping over the edge into the unknowable. Every day, about 20,000 stars slip beyond our cosmic event horizon, becoming forever invisible, forever unreachable. Let's think about this from the perspective of the light itself. A photon emitted from a galaxy just beyond the event horizon is in a tragic situation. It's traveling toward us at the maximum speed possible, the speed of light. But the space between that photon and us is expanding faster than the photon can cross it. From our perspective, that photon is making progress through space at 300,000 kilometers per second. But space is expanding away from us even faster, carrying the photon backward relative to us. The photon is running on a cosmic treadmill. It's sprinting as fast as physically possible, but making no net progress toward us. It's like someone treading water in a river, swimming forward, but being carried backward by the current at the same rate, forever staying in the same place. Except it's worse than that. Because the expansion is accelerating, the photon isn't just staying in place, it's losing ground. It's like trying to run up a down escalator that's speeding up. Even if you're running as fast as you can, you're being carried backward faster and faster. From the photon's perspective, remember, no time is passing. The photon exists in an eternal moment where its emission and absorption are simultaneous. But for us, watching this photon, it's in a purgatory, forever trying to reach us, forever failing. And we can never know it exists. We can never see it. It's forever hidden beyond the edge of what's possible to observe. Now flip the situation. Imagine a photon emitted from Earth, traveling toward a galaxy beyond the event horizon. This photon is also doomed. It will travel forever, never reaching its destination. The galaxy is receding too fast. As the photon travels, the distance to the galaxy increases faster than the photon can cover it. The photon will eventually be stretched by expansion into a lower and lower energy state, its wavelength becoming longer and longer until it's effectively redshifted into oblivion, its energy diluted to nothing across the vastness of expanding space. This is the answer to our central question. No, light cannot escape the universe's edge. Not because there's a barrier that stops it, but because the expansion of space creates a horizon beyond which light can never pass. Light on one side of this horizon and light on the other are forever separated, doomed never to meet, no matter how long they travel. But here's something even more disturbing that I need you to understand. This edge is coming for us. The event horizon isn't static in terms of which objects are inside it. It's static in terms of its distance from us. But because the universe is expanding, galaxies that are currently inside the horizon are being carried by the expansion toward the edge. Eventually, they'll cross it and disappear. Right now, we can see about 2 trillion galaxies in the observable universe. But in the far future, as the expansion continues and accelerates, more and more of these galaxies will slip beyond the event horizon. In a few trillion years, all the galaxies outside our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies gravitationally bound together will have vanished beyond the horizon. Imagine astronomers in that distant future. They'll look out into the night sky and see almost nothing. Just their own local group, maybe merged into a single giant elliptical galaxy by then, surrounded by darkness. They won't see the cosmic microwave background because that radiation will have been redshifted into invisibility. They won't see distant galaxies. They won't see any evidence of the Big Bang. If they try to figure out the nature of the universe using only observations, they'll conclude they live in an eternal, static universe, consisting of just their galaxy, surrounded by infinite empty space. They'll be completely wrong, but they'll have no way to know it. All the evidence of the true nature of the cosmos will have slipped beyond the event horizon, taking the truth with it. This should terrify you intellectually. It means that what we can observe about the universe is contingent on when we observe it. We're living in a special time, a time when the universe is old enough to have formed structures like galaxies and stars, but still young enough that we can see the Big Bang's afterglow and distant galaxies. We can piece together the history of the cosmos because we're observing at the right epoch. But what if we're already too late to see some things? What if there were events, structures, or phenomena in the very early universe that have already slipped beyond our event horizon? What if there are fundamental truths about reality that we can never discover because the evidence has already been carried away by cosmic expansion? This is the tragedy of the cosmological event horizon. It's not just a limit on what we can see. It's a limit on what we can ever know. There are questions we might not even know to ask because the answers have already disappeared beyond the edge. And here's the really mind-bending part. From the perspective of those distant galaxies beyond our event horizon, we're the ones who have slipped beyond their horizon. They can't see us either. If there are civilizations out there, they have no idea we exist, and we have no idea they exist. We're both trapped on opposite sides of an expanding horizon, forever cut off from each other. The universe is fragmenting into causally disconnected regions, islands of space that can never communicate, never share information, never even know the others exist. The universe is becoming an archipelago, with each island completely isolated from the others. And the oceans between the islands are growing, the currents accelerating, making any connection impossible. But let's bring this back to something concrete you can grasp. Remember the cosmic microwave background, that ancient light from 380,000 years after the Big Bang? That light has been traveling for 13.8 billion years to reach us. It started its journey when the universe was a hot plasma, cooling enough for atoms to form and light to travel freely for the first time. That light has been stretched by cosmic expansion from visible wavelengths to microwave waves, a redshift factor of about 1,100. The light was emitted at a temperature of about 3,000 Kelvin, the temperature of a glowing hot surface. Now it's been cooled by expansion to about 2.7 Kelvin, just barely above absolute zero. But here's what's profound. The CMB is also approaching the horizon. As the universe continues to expand and accelerate, the CMB will be redshifted to longer and longer wavelengths. Eventually, in the far future, it will be stretched to radio wavelengths, then to even longer wavelengths, until it becomes undetectable. The cosmic microwave background, the most important piece of evidence for the Big Bang, will fade away into darkness. In that distant future, astronomers will look out and see nothing but their local galaxy surrounded by black emptiness. They'll have no evidence that the universe is expanding, no evidence of the Big Bang, no evidence that there was ever anything beyond their island of stars. The truth of cosmic history will have slipped beyond the horizon, literally redshifted into invisibility. We are living in a privileged moment in cosmic history. We can see the evidence. We can piece together the story. But that window is closing. The universe is hiding its secrets, erasing the evidence, pulling the curtain down on its own history. This brings us to an uncomfortable philosophical question. How much of reality is already hidden from us? How many horizons are there that we don't even know about? What fundamental truths about the cosmos have already slipped beyond our ability to observe, leaving us to construct theories that are incomplete or wrong because we're missing crucial data? Cosmologists worry about this. There's a concept called the lamppost effect, named after the old joke about the drunk looking for his keys under a lamppost. A police officer asks if he lost them there, and the drunk says no, but the light is better here. We study what we can observe, but that doesn't mean it's representative of the whole truth. We're looking under the lamppost because that's where the light is, but the keys might be in the darkness beyond. What if the universe is vastly larger than the observable universe? What if our observable bubble is just a tiny fraction of existence, and the true nature of the cosmos is radically different from what we can see? What if there are other regions with different physical constants, different laws of physics, and we're just stuck in our local neighborhood thinking our rules are universal? Some cosmologists take this seriously. The inflationary theory of the Big Bang, proposed by Alan Guth in 1980 and refined by Andre Linde and others, suggests that the universe underwent a period of exponential expansion in the first fraction of a second. After the Big Bang, this inflation smoothed out the universe and set up the conditions we see today. But here's the kicker. Inflation might not have stopped everywhere at once. It might have ended in some regions, creating bubble universes like ours, while continuing in other regions. This would create an eternal inflation scenario, where our observable universe is just one bubble in an infinite cosmic foam, each bubble potentially having different properties, different laws of physics. If that's true, then the edge of our bubble, the boundary between where inflation ended and where it continues, is another kind of horizon. Light from beyond that boundary could never reach us. We're trapped inside our bubble, observing only our local patch of a much vaster reality. Is this too speculative? Maybe, but it shows how seriously cosmologists take the problem of horizons and edges. We're aware that what we can see might not be all there is. We're aware that the universe might be hiding things from us, not out of malice, but because of the fundamental structure of space-time and the finite speed of light. Let's pause here and take stock. We've established that the universe has an edge, not of space itself, but of observability. This edge, the cosmological event horizon, is a boundary beyond which light cannot reach us, because the expansion of space is faster than light can cross it. We've established that this horizon is real, that it's about 16 billion light years away, and that it's essentially frozen in place while objects are carried past it by cosmic expansion. We've also established that this has profound implications. Thousands of galaxies are slipping beyond this horizon every day, disappearing from our universe forever. In the far future, most of the cosmos will be hidden from us, and future astronomers will have no idea of the true nature of reality. But we haven't yet addressed the question from the photon's perspective. What does it feel like for light to approach this edge? Can a photon sense that it's doomed? What happens to the photon at the moment it crosses the horizon? These questions don't quite make sense because photons don't experience time, but we can ask what an observer would see watching a photon approach the horizon. And the answer is beautiful and strange. Let me ask you something. Have you ever wondered why the night sky is dark? This seems like a stupid question. The night sky is dark because the sun is on the other side of the planet. Duh. But that's not what I'm asking. I'm asking why space itself is dark. Why aren't we bathed in light from all the stars and all the galaxies throughout infinite space? This is called Olber's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who popularized it in 1823. If the universe is infinite, and filled uniformly with stars. Then no matter which direction you look, your line of sight should eventually hit a star. The entire sky should be as bright as the surface of a star. It should be a blazing wall of light. But it's not. It's dark. The resolution of Olber's paradox is the expansion of the universe and the finite age of the universe. The universe is only 13.8 billion years old, so we can only see light from stars within about 46 billion light years. Beyond that, light hasn't had time to reach us yet. And the light we do receive from distant stars is redshifted by cosmic expansion, shifting it toward the infrared and reducing its energy. This is why the sky is dark. Most of the universe is hidden beyond the horizon, and the light from what we can see is weakened by redshift. The darkness of night is direct evidence of cosmic expansion and the existence of a horizon. But here's where things get really interesting. As a photon travels toward us from a distant galaxy, it's getting redshifted by the expansion of space. The farther it travels, the more it's stretched. If the galaxy is close enough that the photon will eventually reach us, we'll see that photon, but it will be shifted toward the red end of the spectrum. Galaxies that are very far away are very redshifted. The most distant galaxies we can see have redshifts greater than 10, meaning their light has been stretched by a factor of more than 10. Light that was emitted as ultraviolet is now observed as infrared. But photons from beyond the event horizon never reach us. They're so redshifted that their wavelength becomes infinite. Their energy becomes zero. They're effectively stretched out of existence. The photon doesn't die or disappear. It's just diluted across infinite space. Its energy spreads so thin that it becomes undetectable. From our perspective, watching a photon approach the event horizon from the other side, we'd see it getting more and more redshifted, its wavelength getting longer and longer, its energy getting lower and lower, asymptotically approaching zero, but never quite reaching it. We'd never see it cross the horizon, because the light from that crossing would be infinitely redshifted. This is very similar to what happens at the event horizon of a black hole. If you watch someone fall into a black hole, you never see them actually cross the event horizon. You see them get closer and closer, but their image gets more and more redshifted, dimmer and dimmer, frozen at the horizon. From your perspective, they never fall in. They're forever frozen at the boundary. But from the perspective of the person falling, they cross the event horizon just fine. Nothing special happens there. They fall through and continue toward the singularity at the center. It's only from the outside perspective that the crossing seems to take infinite time. The cosmological event horizon is similar. A galaxy crossing the horizon from its own perspective does so in finite time. But from our perspective, watching from the other side, the galaxy never quite crosses. It gets dimmer and more redshifted, fading asymptotically, approaching the horizon but never crossing. In both cases, the horizon is a one-way membrane. Things can cross it in one direction, but not return. Information from beyond the horizon can never reach us. Light from beyond the horizon can never reach us. We're forever cut off from what lies beyond. But here's a thought experiment that will bend your mind. Imagine we built a spacecraft and sent it out toward the event horizon. It accelerates, going faster and faster, approaching the speed of light. What would happen? From our perspective on Earth, the spacecraft would get farther and farther away. But as it approached the event horizon, its signals back to us would get more and more redshifted. Eventually, it would cross the horizon and we'd lose contact. We'd see it fade away, its last photons stretched into invisibility. From the perspective of the astronauts on the spacecraft, they'd sail right through the horizon. Nothing special would happen. They'd continue on, exploring the universe beyond. They'd see galaxies we could never see, discover things we could never know, but they could never tell us about it. Any signal they send back would be unable to cross the horizon. They'd be forever cut off from Earth, from humanity, from everything they knew. They would become cosmological pioneers, explorers beyond the edge of the knowable universe. But they could never come home. They could never share their discoveries. They'd be alone in the cosmos, in a region of space forever disconnected from ours. Is this possible in practice? No. We can't build spacecraft that approach the speed of light, and even if we could, the distances involved are absurd. The event horizon is 16 billion light-years away. Even traveling at nearly the speed of light, it would take 16 billion years to get there. The universe would be unrecognizably different by the time you arrived. But the thought experiment reveals something profound. The cosmological event horizon is a point of no return. Cross it, and you can never come back. Send information across it, and that information is gone forever. It's a one-way boundary in space-time, a membrane that information can pass through in one direction, but never return. This makes the event horizon fundamentally different from any edge or boundary in ordinary space. You can walk to the edge of a cliff and come back. You can sail to the edge of the ocean and return. You can fly to the edge of the atmosphere and descend. But the cosmological event horizon is an edge you can cross only once. After that, you're in a different realm of existence, causally disconnected from where you came. In a deep sense, the event horizon is where the universe ends. Not because space ends there, but because causality ends. The laws of cause and effect, which require information to propagate at or below the speed of light, cannot cross the horizon. The universe fragments into separate causal domains, each unable to influence the others. And this fragmentation is accelerating. As dark energy drives the expansion faster and faster, the event horizon is essentially fixed, while more and more of the universe is carried beyond it. The cosmos is being torn apart, not by any force acting on matter, but by the accelerating expansion of space itself. Some cosmologists call this the Big Rip, though that term usually refers to a more extreme scenario where dark energy becomes stronger over time and eventually tears apart galaxies and solar systems and planets and atoms. What we're discussing is less violent, but equally profound. A gradual isolation of all structures in the universe from each other until each galaxy cluster becomes an island universe, alone in an ocean of darkness. Is there any way to prevent this? Can we somehow stop the expansion, or cross the horizon, or preserve information before it slips away? The answer, as far as we know, is no. The expansion of space is not something we can control. It's a property of space-time itself, driven by the energy content of the universe. We're along for the ride, passengers on a cosmic ship heading toward an increasingly lonely future. But maybe, just maybe, there are loopholes. Maybe there are aspects of physics we don't yet understand that would allow communication across the horizon. Maybe quantum entanglement, which allows correlations between distant particles instantaneously, could be used to send information across the horizon. Maybe there are higher dimensions, or wormholes, or other exotic structures that could bridge the gap. These are mostly science fiction right now. Quantum entanglement cannot be used to send information faster than light, as I'll explain shortly. Wormholes, if they exist, would require exotic matter with negative energy to keep them open, and we don't know if that's possible. Higher dimensions are part of string theory, but we have no experimental evidence they exist. But the universe has surprised us before. 100 years ago, we didn't know about the expansion of the universe. 50 years ago, we didn't know about dark energy. 25 years ago, we didn't know the expansion was accelerating. Who knows what we'll discover in the next century? Maybe we'll find a way to probe beyond the horizon. Maybe we'll discover that the horizon isn't as absolute as we think. Or maybe we'll confirm that it is absolute, and we'll have to accept that vast swaths of reality are forever hidden from us. Either way, the question, can light escape the universe's edge, has led us to profound truths about the nature of reality. It's shown us that the universe has boundaries, not in space, but in causality and information. It's shown us that we live in a special time when evidence of the Big Bang is still visible but won't be forever. It's shown us that the cosmos is not static, but evolving, fragmenting, isolating. And it's shown us something even more fundamental. Reality has limits. Not everything can be known. Not all questions can be answered. Some truths are forever beyond our reach, not because we lack the intelligence or technology, but because the structure of space-time itself prevents access. This is both humbling and liberating. Humbling because it reminds us how small and limited we are, how much of existence is hidden from us. Liberating because it means there will always be mysteries, always be unknowns, always be frontiers to explore, even if we can never reach them. Now, take a breath. We're going to shift gears slightly and talk about how all of this affects you personally. Not as an abstract cosmological question, but as a human being living your life right now on this pale blue dot. Because the edge of the universe, as remote and abstract as it seems, has profound implications for meaning, purpose, and how you should live your life. But before we get there, I need you to engage again. Hit that like button if you're still with me. Drop a comment telling me, does the idea of an unreachable edge to the universe make you feel insignificant? Or does it make existence more precious because of its limits? And if you haven't subscribed yet, this is your last warning. We're about to get philosophical, and you don't want to miss what's coming. Let's talk about meaning. You're a conscious being living on a planet orbiting a star in a galaxy of 200 billion stars, in a universe with 2 trillion observable galaxies, most of which will eventually slip beyond our cosmic horizon and vanish forever. You live for maybe 80 years if you're lucky, a cosmic blink of an eye. In 1 trillion years, when most galaxies have disappeared beyond the horizon, the fact that you existed will have left no trace on the universe. So what's the point? This is the question that the cosmological event horizon forces us to confront. If we're isolated in an expanding universe, if we're doomed to eventually be alone in an island of darkness, if everything we do will ultimately be forgotten as the cosmos fragments and fades, does anything we do matter? Some people find this depressing. I think it's the most liberating realization you can have. Here's why. The universe doesn't owe you meaning. Meaning isn't something you discover out there among the galaxies. Meaning is something you create here, now, in your relationships, your work, your curiosity, your kindness. The fact that the universe is vast and indifferent doesn't diminish the meaning you create. If anything, it enhances it. Think about it this way. You watch a movie and it ends. Does the fact that it ends make the movie meaningless while you're watching it? Of course not. The emotional impact, the story, the characters, the moments that make you laugh or cry, they matter while they're happening. The movie doesn't need to be eternal to be meaningful. Your life is the same way. It doesn't need to be eternal to be meaningful. The fact that you'll die, that the sun will eventually explode, that the universe will expand into cold darkness, none of that diminishes the meaning of your life right now. The sunset is beautiful precisely because it's temporary. The moment with a loved one is precious precisely because it will end. The cosmological event horizon, that boundary beyond which light cannot escape, is a metaphor for the limits of existence. Everything has boundaries. Your life has boundaries in time. The observable universe has boundaries in space. Meaning has boundaries too. It exists within contexts, within relationships, within the finite span of conscious experience. And here's the really important part. You are the universe becoming aware of itself. Every thought you have, every moment of consciousness, is the cosmos observing its own existence. You are 13.8 billion years of cosmic evolution, leading to a point where matter has organized itself into a structure complex enough to ask, why? The atoms in your body were forged in the cores of stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar furnaces billions of years ago, scattered into space when those stars exploded, and incorporated into the planet that would eventually give rise to you. You are literally made of stardust. This isn't poetry. It's physics. The carbon, nitrogen, oxygen, and all the heavy elements essential for life were created by nuclear fusion in stars and supernova explosions. You are the universe rearranged into a pattern that can think about itself. And right now, in this moment, you're using that pattern to contemplate the edge of existence, to ask whether light can escape the universe's boundary, to grapple with the nature of cosmic horizons and the fragmentation of space-time. That's extraordinary. That's meaning. Not in spite of your smallness, but because of it. You are small, yes, but you're small in the way a single neuron is small compared to the brain. The neuron isn't meaningless because it's small. It's meaningful because it's part of something larger. You're part of the universe, a small piece, but a piece capable of understanding the whole. And unlike light trapped at the event horizon, unable to escape, unable to communicate across the boundary, you're here now, inside the horizon, part of the connected web of causality that defines our observable universe. You can share ideas, create art, form relationships, influence the future. You're not isolated. You're entangled with everything around you. But there's a darker implication we need to address. If the event horizon is real, if vast regions of the universe are forever cut off from us, what does that mean for the possibility of contact with other intelligent life? The Fermi paradox asks, if the universe is so vast and so old, where is everybody? Why haven't we seen evidence of alien civilizations? There are many proposed solutions, but the cosmological event horizon adds another dimension to the problem. If intelligent life arose in a region of the universe that's beyond our event horizon, we will never know about it. Ever. They're in a causally disconnected region. Any signals they send cannot reach us. Any artifacts they create, any wonders they build, any ideas they have, they're forever hidden from us by the expansion of space. And we're hidden from them. If we sent a message to them, it would never arrive. If we built a monument visible across galactic distances, they'd never see it. We exist in separate realities, both parts of the same universe, but unable to communicate or even confirm each other's existence. This is profoundly lonely. There could be trillions of civilizations out there, each isolated in their own observable bubble, each wondering if they're alone, each unable to reach the others. The universe could be teeming with life, but the expansion of space keeps us all separated, like prisoners in cells that are constantly moving farther apart. And it gets worse. Remember, galaxies are slipping beyond their horizon every day. If there was an advanced civilization in one of those galaxies, and if they were trying to send us signals, those signals would get more and more redshifted as their galaxy approaches the horizon. Eventually, the signals would be stretched into invisibility, and we'd lose contact. Forever. Imagine that. Imagine making contact with an alien civilization, exchanging messages, learning about their culture and science and philosophy, and then watching as the expansion of space carries them away. Their messages come slower and slower, more and more redshifted, until finally they stop. The last message arrives, stretched almost to the point of unreadability, saying goodbye, and then silence. Forever. They're still out there, living their lives, but you can never reach them again. The universe has carried them beyond the edge of the possible. They've slipped into the unknowable. This is the emotional weight of the event horizon. It's not just an abstract cosmological concept. It's a boundary that isolates, that separates, that ensures loneliness on a cosmic scale. But here's the flip side. It makes the connections we do have more precious. You're here on Earth, surrounded by 8 billion other humans, all of us inside the same causal horizon, all of us able to communicate, to share, to connect. We're not isolated. Not yet. We have each other. And we have time. The event horizon is 16 billion light years away. The galaxies that are slipping beyond it right now are so distant that we barely knew they existed in the first place. The galaxies in our local neighborhood, the ones we can see with telescopes, The ones where we might actually detect signs of life, they're not going anywhere. Not for a very, very long time. Our Milky Way galaxy is about 100,000 light years across. Light can easily traverse that distance, even with the expansion of space. In fact, our galaxy is gravitationally bound, meaning the mutual gravity of all the stars and dark matter holds it together against cosmic expansion. The same is true for our local group of galaxies, which includes Andromeda and several dozen smaller galaxies. These galaxies aren't expanding away from each other. They're actually moving toward each other. In about 4 billion years, the Milky Way and Andromeda will collide and merge, forming a giant elliptical galaxy, sometimes called Milkomida. This is happening despite the expansion of space, because gravity is stronger than expansion at these relatively short distances. So even though the distant universe is fragmenting, our local neighborhood is actually coming together. We're not going to be isolated anytime soon. If there's intelligent life elsewhere in our galaxy, or in nearby galaxies, we have billions of years to find them, to communicate with them, to not be alone. This is the time scale we're working with. The expansion of space is accelerating, yes, but it's not fast enough to affect our local region for many billions of years. We have time. The question is whether we'll use it wisely. But let's think even more deeply. The event horizon isn't just about physical isolation. It's about information. The horizon is a boundary beyond which information cannot pass. And if you think about it, information is what reality is made of. Everything you know about the world comes from information. The light hitting your eyes is information. The sound reaching your ears is information. The sensations in your body, the memories in your brain, the words you're reading right now, it's all information. Reality, from your perspective, is the sum total of information available to you. The event horizon is a limit on information. Beyond the horizon, information cannot reach you. In a very real sense, the universe beyond the horizon doesn't exist for you. It's not part of your reality. It's not knowable, not observable, not interactive. It might as well be another universe entirely. This connects to a deep idea in physics, the holographic principle. This principle, proposed by Gerard T. Hooft and refined by Leonard Susskind, suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram where a 2D surface contains all the information needed to reconstruct a 3D image. Applied to the universe, the holographic principle suggests that all the information inside the cosmological event horizon is encoded on the horizon itself. The horizon isn't just a boundary. It's a surface that contains all possible information about our observable universe. This is mind-blowing. It suggests that the 3D space you experience, the depth and volume of the universe, might be an illusion. The fundamental reality might be the 2D surface of the event horizon, and everything inside, including you, is a holographic projection from that surface. I know that sounds like science fiction, but it's a serious idea in theoretical physics, and it has implications for understanding the nature of information, entropy, and the structure of space-time. If the holographic principle is true, then the question, can light escape the universe's edge, takes on a new meaning. The edge isn't a place light is trying to escape from. The edge is where light and all information ultimately resides. The 3D universe is just a convenient description of patterns encoded on the 2D horizon. This is speculative, and I'm pushing into the frontiers of current research, but it shows how deeply the concept of horizons and edges is woven into modern physics. The boundary between what can be observed and what cannot isn't just a practical limit. It might be a fundamental feature of how reality is structured. Let's bring this back to Earth, literally. You're sitting somewhere on this planet, reading or listening to these words, contemplating the edge of the universe. How does any of this affect your daily life? Here's how it changes your perspective. Knowing about the event horizon, about the fragmentation of the universe, about the temporary nature of our observable cosmos, It gives you a cosmic perspective. It's what astronauts call the overview effect, the cognitive shift that happens when you see Earth from space and realize how small and fragile and interconnected everything is. You don't need to go to space to have that realization. You can have it right now, thinking about cosmic horizons and the edge of light's reach. You're part of something vast and temporary and beautiful. Your problems, your worries, the things that keep you up at night, they're real and they matter, but they're also tiny compared to the scale of the cosmos. This isn't meant to diminish your problems. It's meant to give you perspective. The argument you had with your partner, the deadline at work, the anxiety about the future, these things are important because they affect your immediate experience. But they're not ultimate. They're not cosmic. They're human scale, and that's okay. In fact, it's more than okay. It's perfect. You're not supposed to solve cosmic scale problems. You're supposed to live your human scale life, to find meaning in the small moments, the connections with others, the beauty of a sunset, the satisfaction of a job well done, the love of family and friends. The universe is vast and expanding and fragmenting, and you're here now, alive, conscious, able to appreciate the enormity of it all. That's the gift. That's the meaning. Not cosmic immortality, but present awareness. Here's a thought experiment. Imagine you could live forever. Imagine you were immortal, able to survive the death of the sun, the collision of galaxies, the heat death of the universe. Would that make your life more meaningful? I don't think so. Immortality would make every moment less precious because you have infinite moments. The specialness of now would be diluted by the certainty of forever. Meaning comes from scarcity, from finitude, from the knowledge that this moment will not come again. The cosmological event horizon is the universe's finitude writ large. Just as your life has a beginning and an end, the observable universe has a boundary beyond which it cannot communicate. Just as your individual moments are precious because they're fleeting, the universe's current state is precious because it's temporary. Future astronomers won't see what we can see. We're living in a golden age of cosmology, when the evidence of the Big Bang is still visible, when distant galaxies haven't yet slipped beyond the horizon. We're lucky. We're living at just the right time to understand the cosmos. 1 trillion years from now, that understanding would be impossible. The evidence would be gone. We are here now, able to piece together the story of existence. That's extraordinary. And you're part of that. By learning about the universe, by thinking about these questions, by engaging with the deepest mysteries of existence, you're participating in the universe's self-awareness. You're a node in the network of conscious beings trying to understand it all. This is why education matters. This is why science matters. This is why curiosity matters. We're in a race against cosmic expansion, trying to understand the universe before the evidence slips away. We have billions of years, but that's not forever. At some point, the last galaxy will cross the horizon. The last piece of evidence will be redshifted into invisibility, and the universe will have hidden its secrets. Our job as conscious beings is to look while we can, to learn while we can, to understand while we can, and then to pass that understanding on to the next generation so they can continue the quest. This is the meaning of the human project. We're not here to conquer the universe, or live forever, or transcend our limitations. We're here to witness, to understand, to appreciate. We're the universe's way of knowing itself. And that's enough. That's more than enough. That's everything. Now, I want to shift to something that might seem contradictory. I've been talking about isolation, about boundaries, about how the expansion of the universe fragments it into causally disconnected regions. But there's another aspect of quantum mechanics that suggests a different kind of connection, one that might transcend space itself. I'm talking about quantum entanglement. You've probably heard of this. Two particles can become entangled, meaning their properties are correlated in a way that persists no matter how far apart they are. Measure one particle, and you instantly know something about the other particle, even if it's on the other side of the universe. Einstein called this spooky action at a distance, and he thought it showed that quantum mechanics was incomplete. How could two particles be connected instantaneously across vast distances? Doesn't that violate the speed of light limit? The answer is subtle. Quantum entanglement does create instantaneous correlations, but it cannot be used to send information faster than light. Here's why. When you measure an entangled particle, you get a random result. Let's say you have two entangled electrons, one on Earth and one on a distant planet. Each electron has a property called spin, which can be either up or down. Before you measure, the spin is undetermined. The electron is in a superposition of both up and down. When you measure your electron on Earth, it randomly collapses to either spin up or spin down, 50/50 odds. At that instant, the distant electron's spin is determined to be opposite. If yours is up, theirs is down, and vice versa. This happens instantaneously, faster than light. But here's the thing. You can't control which result you get. It's random, so you can't encode a message in the results. The person on the distant planet sees their electron spin, but from their perspective, it's just a random up or down. They have no way of knowing whether you've measured your electron yet. The correlation only becomes apparent when you compare results after the fact, which requires classical communication at or below the speed of light. So quantum entanglement is real, and it does create instantaneous correlations, but it doesn't allow faster-than-light communication. The correlations are there, but they're useless for sending information until you bring the results together through normal, slower-than-light channels. This means entanglement cannot be used to communicate across the cosmological event horizon. Even if you had entangled particles on both sides of the horizon, you couldn't use them to send messages. The entanglement would persist, in principle, but you couldn't exploit it for communication. Or could you? There's a speculative idea in physics that entanglement might be related to the structure of spacetime itself. Some physicists, like Juan Maldacena and Leonard Susskind, have proposed that entanglement and spacetime geometry are deeply connected, encapsulated in the phrase I equals EPR, which suggests that quantum entanglement, EPR, is equivalent to wormholes, Einstein-Rosen bridges, connecting distant points in spacetime. If this is true, then entangled particles might be connected by microscopic wormholes, tiny tunnels through spacetime. And if wormholes connect entangled particles, maybe macroscopic wormholes could connect distant regions of the universe, even across the event horizon? This is wild speculation, and there's no experimental evidence for it, but it's a tantalizing possibility. If wormholes exist and can be stabilized, they might provide a way to communicate or travel across regions of space that are otherwise causally disconnected by cosmic expansion. But even if wormholes exist, using them would require exotic physics. You'd need negative energy or exotic matter to keep the wormhole open, and we don't know if that's possible. You'd need to control the wormhole's endpoints, placing one inside the event horizon and one outside. And you'd need to ensure the wormhole doesn't collapse or become unstable. These are enormous challenges, and they might be impossible. But the universe has surprised us before. A century ago, we didn't think black holes were real. They were a mathematical curiosity, a strange prediction of Einstein's equations that surely didn't exist in nature. Now we've photographed them. We've detected gravitational waves from black hole mergers. We know they're real. Maybe wormholes will be the same. Maybe in a century, we'll have evidence for them, or maybe we'll have a proof that they can't exist. Either way, the question is open. But even if wormholes are impossible, even if there's no way to cross the event horizon or communicate beyond it, the fact that we can ask these questions is remarkable. We're not just passive observers of the universe. We're active participants in understanding it. We push the boundaries of knowledge. We test the limits of possibility. We imagine what might be. That's the human spirit. That's what makes us unique. We don't just accept the universe as it is. We question it, we probe it, we try to understand it. And even when we hit limits, even when we find boundaries we cannot cross, we don't stop. We keep asking why. The cosmological event horizon is a boundary, yes, but it's also a challenge. It's the universe saying, "This is as far as you can see." And we respond, "But can we see farther? Can we find a loophole? Can we learn something new that changes the rules?" Sometimes the answer is no. Sometimes the boundary is real and absolute. But sometimes the answer is yes. Sometimes we find a way through, a new perspective, a different approach. That's the history of science. That's the history of human exploration. And even when we can't cross the boundary, we learn something by reaching it. We learn about the structure of reality, about the limits of possibility, about the nature of existence. The journey to the edge is valuable, even if we can't go beyond. So here's what I want you to take away from this. The universe has an edge, not of space, but of causality and information. Light cannot escape this edge because the expansion of space prevents it. This edge is real, measurable, and has profound implications for the long-term future of the cosmos and the possibility of contact with distant life. But this edge doesn't diminish you. It doesn't make your life meaningless. If anything, it makes your existence more precious because you're here, now, inside the horizon, part of the connected web of causality that defines our observable universe. You're not isolated. You're entangled with everything around you. And you have the privilege of living at a time when we can see the evidence, when we can piece together the cosmic story, when we can understand the nature of the edge. Future generations might not have that privilege. The universe is hiding its secrets, pulling down the curtain. But right now, the stage is still lit. The show is still on. And you're part of the audience. So pay attention, be curious, ask questions, engage with the mysteries. And remember that your smallness in the cosmic scale doesn't diminish your importance. You're a part of the universe that can think about itself. That's not insignificant. That's miraculous. Before we move on to our final sections, I need you to engage one more time. Leave a comment telling me, has this changed how you think about your place in the universe? Do you feel more connected or more isolated? And if you found value in this, hit that like button and subscribe. We're in the home stretch, but the best is yet to come. Now, let's talk about the future. What happens to light, to information, to the universe itself in the far future as the expansion continues and the event horizon remains fixed while more and more galaxies slip beyond it? Cosmologists have thought carefully about this. The far future of the universe depends critically on the nature of dark energy. If dark energy remains constant, as current evidence suggests, then the universe will continue expanding forever, with the expansion rate asymptotically approaching a constant value. This is called the de Sitter universe, named after the Dutch physicist Willem de Sitter, who first studied this solution to Einstein's equations. In a de Sitter universe, the event horizon remains at a fixed distance, about 16 billion light years. Galaxies beyond this horizon recede faster than light and can never communicate with us. Over time, more galaxies cross this horizon and disappear from view. In about 100 billion years, all galaxies outside our local group will have crossed the horizon. The night sky will be dark, with only the stars in our own merged galaxy visible. The cosmic microwave background will have been redshifted into invisibility. In 1 trillion years, the last stars will burn out. The universe will consist of dead stellar remnants, white dwarfs, neutron stars, black holes. These objects will slowly evaporate through a quantum process called Hawking radiation, but this takes an incomprehensibly long time. A solar mass black hole takes about 1,067 years to evaporate. In 10,100 years, even the largest black holes will have evaporated. The universe will consist of a thin soup of elementary particles. photons, neutrinos, electrons, positrons, moving apart from each other as space continues to expand. The temperature of space will asymptotically approach absolute zero. This is the heat death of the universe, the ultimate equilibrium state where no work can be done, no structures can form, no complexity can exist. It's a cold, dark, empty future, with particles separated by ever-increasing distances, unable to interact, unable to form anything interesting. And light? Light will still be there, but infinitely redshifted, stretched to wavelengths larger than the observable universe itself. Photons that are now visible light will have wavelengths of light years. They'll be so low in energy that they're effectively nothing, indistinguishable from the vacuum itself. This is the fate of light that tries to escape the universe's edge. It doesn't hit a wall. It doesn't disappear. It just fades, stretches, dilutes, until it's no longer meaningfully light at all. It becomes part of the cold, dark, empty space. Is this depressing? Maybe, but it's also liberating. It means the universe doesn't last forever, in any meaningful sense. The heat death is essentially the end of time, because nothing changes after that. There's no more evolution, no more events, no more history. Time becomes meaningless when nothing happens. This gives our current epoch meaning. We're living in the brief window of cosmic history, when interesting things happen, when stars shine, when planets form, when life emerges and asks questions about existence. This window is maybe 1 trillion years long, out of an infinite future of cold emptiness. We're in the golden age, the brief flicker of light and warmth before the eternal darkness. And that makes now matter. The universe doesn't last forever, so what happens now is all there is. Your life, your choices, your relationships, they're happening in the only era of cosmic history when anything matters. After the heat death, there's nothing. No one to remember, no structures to persist, no meaning to be found. But now there's everything. This is the existential weight of cosmology. Understanding the universe's future forces you to confront the temporary nature of existence. But it also forces you to appreciate the present, the brief window of possibility we're lucky enough to inhabit. Some cosmologists have proposed that the heat death might not be the end. Maybe quantum fluctuations could spontaneously create new structures, new universes, new moments of order out of the chaos. Maybe the universe undergoes cycles of expansion and contraction, big bangs followed by big crunches, repeating eternally. Maybe there are other universes, other branches of the cosmic tree, where different histories play out. These are speculative ideas, and we have no way to test them. But they show that even when facing the end of everything, humans keep imagining possibilities, keep asking, what if? Keep refusing to accept finality. That's the human spirit again. We don't accept limits. We question them, probe them, imagine ways around them. Even the heat death of the universe doesn't stop us from asking whether there's something beyond. But let's be honest, from our perspective, the heat death might as well be the end. Even if something comes after, it's so far in the future, so disconnected from now, that it's irrelevant to us. We won't be there. Nothing we do now will affect it. The universe after the heat death, if there is one, will have no memory of us, no trace of our existence, no connection to our time. So what do we do with that knowledge? How do we live meaningful lives in the shadow of cosmic futility? Here's my answer. We stop looking for meaning in the cosmos and start creating meaning here, now with each other. The universe doesn't provide meaning. We do. Meaning is a human phenomenon, a product of conscious minds interpreting their experience and deciding what matters. You decide what matters. Not the universe, not God, not fate. You. Every day, you make choices about what to care about, who to love, what to work toward. Those choices create meaning. They don't need cosmic validation. They don't need to last forever. They just need to matter to you now. the cosmological event horizon, the heat death, the fragmentation of the universe. These are facts about physical reality. But your life isn't just physical reality. It's subjective experience, consciousness, feeling, meaning. And those things exist in a different domain than cosmic expansion. Yes, you're made of atoms that obey physical laws. Yes, you're embedded in a universe governed by space-time curvature and quantum mechanics. But you're also a subject, a locus of experience, a place where the universe becomes aware of itself. And that awareness creates something new, something that doesn't reduce to physics alone: meaning, value, purpose. This is what philosophers call the hard problem of consciousness. How do physical processes give rise to subjective experience? We don't know. Maybe consciousness is fundamental, a basic feature of reality like space and time. Maybe it emerges from complex information processing. Maybe it's an illusion, though that seems self-contradictory. An illusion requires someone to be fooled. Whatever the answer, consciousness is real for you. Your subjective experience is the most immediate, undeniable fact of your existence. I think, therefore I am, as Descartes said. You might doubt everything else, but you can't doubt that you're experiencing doubt. And that experience, that consciousness, is where meaning lies. The universe might be indifferent, but you're not. You care about things. You value things. You find beauty in sunsets, and joy in laughter, and meaning in love. Those aren't physical facts about the universe. They're facts about your experience of the universe. So the answer to can light escape the universe's edge is no physically, but yes, metaphorically. Light, as in understanding, as in consciousness, as in meaning, transcends the physical boundaries. You're not trapped by the event horizon because you're not just a physical object. You're a subject, an observer, a creator of meaning. The edge of the universe is a limit on physical causality, but it's not a limit on what you can think about, imagine, create. You can conceive of what's beyond the horizon, even if you can't observe it. You can imagine the far future, even if you won't experience it. You can create meaning in the present, even if that meaning won't persist forever. This is the power of consciousness. It's not bound by the same limits as light. It can escape the edge in ways that photons cannot. All right, we're approaching the end of our journey. We've explored the nature of light, the expansion of the universe, the cosmological event horizon, the fate of the cosmos, and the meaning of existence in the face of cosmic limits. We've met scientists like Ole Rachmer, Edwin Hubble, George Gamow, and countless others who've contributed to our understanding. We've grappled with the reality that most of the universe will eventually be hidden from us, that light cannot escape beyond the event horizon, that we're living in a brief golden age of cosmic awareness. Now I want to bring it all together with one final mind-bending idea that will change how you see reality forever. Are you ready? Here it is. You are light that has escaped the universe's edge. Let me explain. When the universe was very young, during the first few minutes after the Big Bang, it was a hot, dense soup of particles and radiation. Photons couldn't travel freely because they were constantly scattering off charged particles. The universe was opaque, like a thick fog. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons could travel freely. The fog cleared. Light escaped for the first time. That light is the cosmic microwave background, and we can see it today, redshifted by 13.8 billion years of cosmic expansion. But here's the thing. Those photons have been traveling through space for all that time. They've crossed vast distances, traversed the expanding universe, and finally, after an incomprehensibly long journey, some of them reach Earth. And when they do, they hit detectors we've built. Telescopes, satellites, instruments designed to catch them. And through those instruments, through our analysis and understanding, those photons become part of human knowledge. They become part of our map of the cosmos. But you're not just a passive receiver of photons. You're an active participant in the universe's self-awareness. The photons that hit your eyes from distant stars, from the sun, from this screen you're reading, they're carrying information. And your brain processes that information, creates a model of reality, generates consciousness. You are the endpoint of light's journey. You are where photons come to be observed, to be understood, to mean something. And in that sense, you are light that has transcended the physical limits of the universe. You've transformed photons into understanding, energy into meaning, physics into consciousness. This isn't metaphor. This is literally what's happening right now. Photons are entering your eyes, striking your retinas, triggering neural signals, being processed by your visual cortex, integrated into your conscious experience. The light from distant stars has traveled for billions of years to reach you, and you're the one who gives it meaning. The universe has an edge that light cannot physically cross. But light has an endpoint that transcends the physical. You and every other conscious being. You are where light goes to be transformed into something more than mere energy. You are the universe's way of mattering. And here's the truly profound part. When you share what you've learned, when you tell someone about the cosmic event horizon, or the nature of light, or the expansion of the universe, you're propagating that understanding. You're sending light, metaphorically, out into the world. And that light, that knowledge, can travel farther and faster than any photon, because it's carried by language, by culture, by the collective endeavor of conscious beings trying to understand. Books, videos, conversations, art, they're all ways of transmitting light in this metaphorical sense. You're part of a network of understanding that spans the globe and reaches across generations. You're connected to every human who's ever looked up at the night sky and wondered, every scientist who's ever calculated the universe's expansion, every philosopher who's ever grappled with the meaning of existence. This network of understanding is how light escapes the universe's edge. Not physically, but informationally. The universe understands itself through us, and that understanding is not limited by cosmic horizons or the speed of light. It's limited only by our curiosity, our courage, our willingness to engage with the deepest mysteries. So when you ask, can light escape the universe's edge? The answer is paradoxical. Physically, no. Information cannot propagate faster than light, and light cannot cross the cosmological event horizon. But metaphorically, spiritually, intellectually, yes. Light escapes through understanding, through consciousness, through beings like you who transform photons into meaning. You are the edge of the universe where light goes to transcend itself. You are the boundary between the physical and the meaningful. You are the place where cosmic evolution becomes conscious awareness. And that is why you matter. Not because you'll last forever, not because the universe depends on you, but because you're the universe's only chance to understand itself before the evidence slips away, before the galaxies cross the horizon, before the heat death makes everything meaningless. You're living in the golden age, the brief window when understanding is possible, and you're doing it. You're here now, engaging with the deepest questions existence has to offer. You're fulfilling your cosmic purpose, even if you didn't know you had one. So here's my final message to you. Don't waste this. Don't spend your life distracted by trivialities, numbed by routine, disconnected from the wonder of existence. You're a pattern of matter and energy that can think about itself. You're a way for the universe to experience its own beauty, its own complexity, its own mystery. Look up at the night sky. Those photons hitting your eyes have traveled across space and time to reach you. They've escaped the hearts of distant stars, traversed the void, survived the journey, and now they're part of your experience. You're connected to the cosmos in the most direct possible way. And when you share what you've learned, when you tell someone about the event horizon or the expansion of the universe or the nature of light, you're continuing the chain. You're passing the light forward. You're ensuring that the universe's self-awareness persists, even as the physical cosmos fragments and fades. This is the real answer to whether light can escape the universe's edge. It can't, physically, but it already has, metaphorically, through you. You are the escaped light. You are the understanding that transcends physical limits. You are the meaning that emerges from meaningless atoms arranged in an improbable pattern. And that's beautiful. That's profound. That's enough. Thank you for taking this journey with me. Thank you for engaging with these ideas, for thinking deeply about existence, for being part of the universe's grand project of self-understanding. You've spent over 3 hours exploring one question, and I hope you found answers that resonate. But more than answers, I hope you found new questions. I hope you're more curious now than when you started. I hope you look at the world differently, see your place in the cosmos with fresh eyes, feel connected to something larger than yourself. Because that's what understanding does. It doesn't close doors. It opens them. Every answer reveals new mysteries. Every solved problem points to deeper puzzles. The more we know about the universe, the more we realize how much we don't know. And that's perfect. That's how it should be. If we ever reached a point where we understood everything, where no questions remained, existence would be boring. The fact that mysteries persist, that horizons limit us, that we can never know everything, that's what makes the quest meaningful. So keep questing. Keep asking questions. Keep looking up at the night sky and wondering. Keep sharing what you learn with others. Keep being a node in the network of understanding that spans humanity. You are light that has escaped the universe's edge. You are consciousness emerging from cosmic evolution. You are meaning manifesting in a vast, indifferent cosmos. And you are enough. Before we close, I want you to do one final thing. Leave a comment telling me, what question do you have now that you didn't have before? What do you want to explore next? Where will your curiosity take you? And if you found value in this journey, if you feel different now than you did 3 hours ago, hit that like button one last time. Subscribe to the channel so we can continue exploring the deepest questions together. Share this video with someone who needs a cosmic perspective, who could benefit from seeing their place in the grand scheme of things. We're all in this together, living in this brief golden age of cosmic understanding. Let's make the most of it. Let's be the light that escapes, the meaning that emerges, the consciousness that transforms the universe's raw physics into something beautiful and profound. Thank you for being here. Thank you for thinking. Thank you for being part of something larger. Now go out there and live like you're a piece of the universe that can think about itself, because you are. And that's miraculous. The edge is real. Light cannot cross it physically, but you've already crossed it in every way that truly matters. This is the end of our journey, but it's the beginning of yours. Take what you've learned and run with it. Transform it into action, into kindness, into curiosity, into meaning. The universe is waiting for you to understand it.